So continuing on with section 6.2, we're looking again at the different ways to solve various different probability problems. And I had wrote this list again because we're going to go back to it over and over again. But these are the 5 ways that we're going to talk about in chapter 6 to solve a variety of probability problems. So we've already talked about simulation. We did that in section 6.1. We just talked about Venn diagrams and tree diagrams, and we'll certainly revisit these a little bit later on too. I want to finish up by tackling enumeration, and then we're going to tackle rules of probability. So enumeration is our next one. It basically just means list out all possible outcomes. To enumerate just means to make a list. So a synonym or another word for enumeration is finite probability table. And the word finite means not infinite, right? So there's only a certain number of things, which is why we actually can list them all out, because the number of possible outcomes is finite. It's relatively small. So here's just a silly example. So it says, you roll 2 dice, what's the probability of getting a prime number? Well, first of all, when you think about you roll 2 dice, how many possible outcomes are there? Well, there are 6 on the first die and 6 on the second die. And so 6 times 6 is 36. Now 36 is not that big of a number, right? We actually can list out all 36 outcomes. And there are those 36 outcomes. I just wrote them all there. It's a little bit tricky because you have to realize that actually you may think, well, isn't the outcome 1, 3 and 3, 1 the same outcome? But actually no. Think about what you got on the first die and what you got on the second die. So here we go. The probability of getting a prime number is going to end up being something over 36 because there are 36 possible outcomes. Well, now let's just go ahead and circle all the outcomes that represent prime numbers. Well, 3 is a prime number. 1 plus 2 is 3. 5 is a prime number. 7 is a prime number. There's 7, there's 5, there's 3. There's 5, 6, 7, 8, 9 is not. There's 5, 7, 9 is not. There's 10. There's 7. 9 is not. There's 11. There's another 11. And then there's a 7. There's a little kind of pattern to it, huh? So I've enumerated all the ones that are prime. And now how many are there? Well, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I get 14 out of the 36 outcomes are prime numbers. And of course, would probably reduce that to, I don't know, maybe 7/18. Okay? And that's just a simple example of enumeration. Why could we do it with enumeration? Because there were only 36 outcomes, and that's just not that big of a number. Okay, here's another kind of sillier example. So let's say Jack and Jill are playing some kind of card game. And so basically Jack is going to randomly draw a card, Jill is going to randomly draw a card, and they're going to decide whoever gets the biggest number wins. So Jack has 4 possible cards. For some reason the cards are -1, 0, 7, and 12. Jill only has 3 cards, a -3, 8, and 9. And so we want to find the probability that Jack beats Jill. Well, again, how many possible outcomes are there? There's just not that many, right? There's actually only going to be 12. And so we can actually go ahead and list those 12 outcomes. And that's exactly what I just did. I listed out the 12 outcomes. And we want to know what's the probability that Jack beats, that's a greater than, Jill. Well, it's going to be something over 12 because there are 12 possible outcomes. And all we have to do, the first number always represents Jack. Second number represents Jill. Just let's list out what are the outcomes where Jack beats Jill. Well, -3 is the smallest number, so it's going to be all of these numbers are a case where Jack beats Jill. Okay. We want the bigger number to be, so this one is true, and this one. I think that's it, right? In every other case, the second number is bigger. Is that true? Yes. Okay, so how many of those situations did Jack beat Jill? 1, 2, 3, 4, 5, 6. So 6 out of 12, and that ends up being 1/2. Okay. Again, why could I use enumeration? Because there were only 12 possible outcomes. Okay, this leads to another idea. This leads to another idea called the multiplication principle, which actually we've been using all along. And so basically it's the idea that if A has m possible outcomes and B has n possible outcomes, then A and B together have m times m possible outcomes. We just saw that in my previous 2 examples, right? Where did I do the 6 times 6 equals 36? Because there were 6 possible outcomes for the first die, 6 for the second die. There were 36 outcomes overall. Okay, in the one before that, I did 4 times 3 equals 12. There were 12 possible outcomes because Jack had 4 cards and Jill had 3 cards. This is an idea you've seen before. If I imagine I flip a coin and then draw a card, how many possible outcomes are there? Well, it's going to be flipping a coin, there are 2 possible outcomes. Picking a card, there are 52 possible outcomes. There would be 104 possible outcomes. That's just it's called the multiplication principle. And as long as we're here, just throw in one other new vocabulary word, and it's the term with replacement or without replacement. And it comes up sometimes when you're drawing cards. The question is, do you put the card back in the deck? So for example, if you draw a card without replacement, that means you draw a card, and then you draw the second card from the 51 cards that would be left in the deck. Whereas if you draw a card with replacement, you would draw a card, look at it, and put it back in the deck. So if the second card is kind of the question, right? If you do it with replacement, all 52 cards are the end. You could draw the same card twice. Whereas if it's done without replacement, the second card, there's 51 possible outcomes because one card's already been drawn. For the third outcome, you've already drawn 2 cards, there'd be 50 possible outcomes. You'll just see these terms from time to time, and I just want to make sure you understand what they mean. Okay, now you've seen this list before. This is, again, I'm kind of going over and over again, the 5 different ways we are going to solve probability problems. I think at this point we've actually tackled the first 4, right? We did simulation in section 6.1. We just did these 2. We just talked about enumeration. So now we're ready to tackle the last one, which is rules of probability. And this is when you think about, this is the kind of the most mathematical, maybe. This is like the formulas, if you will, for rules of probability. And I've saved it for last because I think this is actually the hardest one. And I think if you can avoid using rules of probability, you should try to think about doing it one of the first 4 ways. Because people tend to get bogged down a little bit with rules of probability because it's a little bit more kind of abstract manipulation. You're talking about these kind of formulas. And I think oftentimes with probability, try to just use the first 4 ways, which are kind of more commonsensical than the kind of arcane notation and formulas that we're going to talk about in rules of probability. But they're not that scary, and basically all we're doing is we're putting some notation to some ideas that I think will make some sense. Okay, so let's talk about these rules. Well, it turns out there's going to be 5 different rules of probability. These are the 5 formulas for using the 5th way. And the first one is actually pretty straightforward. We're going to say probability of A, that's some event. Well, that has to be between 0 and 1, inclusive. Okay, so that's all that's saying is probability, when you think about any probability of any event, it's some number between 0 and 1. Of course, 0 itself would be an event that could never happen. 1 would be an event that would always happen. So there's our first rule of probability, just the probability of A is a number between 0 and 1. Second rule, this S, by the way, stands for sample space. And remember, the sample space is the list of all possible outcomes, or the set of all possible outcomes. So all this is a fancy way of saying the probability that something happened is 1. Okay? When you think about when you flip a coin, what's your sample space? Well, it's heads and tails. So what's the probability of getting either a head or tail? Well, it's 1, right? If you roll a die, what's the probability of getting a number 1, 2, 3, 4, 5, 6? It's 1. Probability of something happening is 1. Okay? That's 2 of our 5 rules. Probably the easiest 2. Okay, our next rule is something called the addition rule. And the addition rule has to do with the symbol OR. Okay, and actually what you'll notice I've done is I've introduced a new symbol, which is this big upside down, or this big horseshoe, excuse me. The horseshoe symbol is union, and it's a synonym for OR. So I've written this kind of equation twice, once using the English word OR, and once using the big union horseshoe symbol. And the probability of A or B happening is the probability of A plus the probability of B. That's why it's called the addition rule, because there's the plus for the addition rule, right? So you can kind of think about this rule, what's the probability of drawing a, 2 or a jack from a deck of playing cards, right? Or what's the probability that someone has blue eyes or has brown eyes, okay? Now, this is an important condition down here that I've written. This formula only works if A and B are disjoint. Remember that the term disjoint means cannot happen at the same time, okay? And in section 6.3, we'll talk about kind of a modified version of the addition rule. What if they are not disjoint? But for right now, I'll probably always give you disjoint events. Don't use this formula if A and B are not disjoint. Okay, the addition rule. Our next one is something called the complement rule. Okay, And remember, this symbol means A complement. It's the probability that A did not happen. And it just makes sense, right? It's 1 minus the probability of A happening. So just, if there's a 10% chance that someone has blue eyes, what's the probability that someone does not have blue eyes? Well, it's 1 minus 10% would be 90%, right? What's the probability when you roll a die that you do not get a 4? Well, the probability of not getting a 4 is 1 minus the probability of getting a 4. It would be 1 minus 1/6 would be 5/6. Okay? That's the complement rule. Remember, the little c stands for complement. Our last rule is something called the multiplication rule. Okay? And the multiplication rule, again, I'm going to do what I did before. I've written it two ways. I've used and here, and then I've written this upside down horseshoe. This is pronounced intersection, and it's a synonym for and. So if you see and the upside down horseshoe, they mean exactly the same thing. We pronounce this and or intersection. And the probability of A and B, or A and B, is probability of A times the probability of B, right? It's called the multiplication rule because this is A times. And like before, I kind of give you a caveat, which is only use this formula if A and B are independent. Remember, independent means one outcome does not influence the other. Okay, like if you draw imagine I'm going to roll a die and flip a coin. What's the probability of getting a 3 and heads? Well, that would be the excuse me, what happened there? That's weird. The probability of getting a 3 and heads would be the probability of getting a 3 times the probability of getting a heads would be 1/6 is the probability of getting a 3. 1/2 would be the probability of getting heads. Well, that's 1/12. And again, only use this if these things are independent. Well, sure, coin flips and rolling a die do not affect the other in any way, so they are independent of each other. Okay, I rushed through those rules of probability pretty quickly. I want to do a little bit more of an extended example involving the rules of probability, because I think these probability rules can get a little bit hard. This is a typical kind of probability problem. You've got a strand of Christmas lights, 30 lights in a row, and the way Christmas lights at least used to work is that if one light bulb burns out, the whole strand doesn't work. So let's say each bulb has a 2% probability of being burnt out, and if any one bulb burns out, the whole strand's dead. Find the probability that the strand does work. Okay? Well, so you have to kind of think about what does this have to do with each other. First of all, would it make sense that each bulb burning out is independent? Yeah. So let's first of all say, okay, using rule 3, what's the probability of a bulb working? Well, that's going to be 1 minus the probability of the bulb not working, which is going to be 1 minus 0.02, which is said in the problem is 0.98. I just got that number by using rule 4, wasn't it? The complement rule. Okay. Now think about this. What's the probability of the first bulb working and the second bulb working? Well, aren't those bulbs independent? So I can use the fifth rule, the multiplication rule. That's going to be 0.98 times 0.98. Okay, whatever that number is. In fact, you think about it for a second, what's the probability of the first bulb and the second bulb and the third bulb of all the bulbs working? Is going to be 0.98 times 0.98. Wouldn't you have 30 of those, which would end up being 0.98 to the 30th. Again, I'm using the multiplication rule, but here I'm multiplying 30 different numbers together, which ends up being about 0.5455. And this is actually the answer to the question. Because think about it, the probability of all bulbs working, isn't that the same thing as the whole strand working? I mean, I kind of wrote the same thing here. So our answer to this question, using all the different rules, is 0.5455. It's a little bit intuitively backwards, because a lot of you, if I had not done it this way, probably would have just said, oh, it's just 30 times 0.2 and maybe 1 minus that. We have to kind of think about the rules of probability cleverly. I think that's kind of a good example of why it's a little bit hard. And we'll do lots more examples of these rules of probability.